Hello, in this presentation I will talk about the applications of the most important thermal analysis in food science and technology. First I will talk several things about thermal analysis, and then I will explain with more detail these four techniques. So thermal analysis are techniques that allow to study certain physical parameters of materials as a function of temperature. It means that with, for example, heating or cooling processes, several changes occur. And through the measurement of these changes, one could learn several things about these materials because these changes are typical or characteristics of each material. These analyses are commonly used in polymers, but they can be applied in other types of materials, including manufactured products such as foods. In the example, we could see melting cheese that is used in fondue. Well, this thermal analysis will be based on the measurement of different properties. For example, thermogravimetry is focused on the measurement of mass changes, while um, DTA or DSC are based on the measurement of temperature or heat flows, while the measurement of other parameters such as dimensions are the main focus of TMA and DMA. In this table, we can learn the principle of each of these four techniques and what type of information one can get from the analysis. For example, in TGA, what the technique measures is changes in weight due to changes in temperature. This could be done in either inert or reactive atmospheres. What information could be obtained from them? For example, thermal stability of a material, or in the case of foods, it will be useful to determine the shelf life of a product. It could also be coupled with other techniques such as gas chromatography or infrared in order to obtain more information, especially the chemical composition or identification of the components of these materials. In the other techniques, such as DSC, some things are similar, but the measurements are done under different circumstances. For example, in DSC, what is monitored in the technique is the difference in temperature between a sample and a reference material as a function of time and temperature in a specific atmosphere. Later, we will explain more things about these techniques. Here, we could see what type of applications are derived from each of these thermal analysis methods. For example, if one would like to learn something about the thermal stability of a food product, the techniques that are normally occupied are TGA and DSC. Regarding protein denaturation, for example, the most common technique will be DSC. And finally, in this table, it is possible to learn what type of samples are processed by each of these techniques and which properties could be studied. In this case, for example, if one is interested in the reactivity of a product, the samples will be in chemicals, elastomers, plastics, textiles, and metals, for example. Okay, moving to thermogravimetric analysis, which is commonly represented by the letters TGA. Some details. For example, few milligrams of sample are necessary to process. This material will be put in a thermobalance, which is very sensitive and have heating elements, which will act, as the name indicates, heating all these furnace. Um, a purge gas will be used, and this one could vary according to the type of environment that is meant to be. For example, nitrogen, argon, or helium could be used if an inner environment is desired. Air or oxygen if an oxidizing environment is required, or this mixture of hydrogen in nitrogen if reducing conditions are required. Also, the humidity of the gas could vary from very dry conditions to saturated ones. Regarding the heating programs, they could be dynamic, in which case the temperature is increased linearly over time in a constant rate, or isothermal, in which case the temperature is fixed during a certain period during the test. And also, it is possible to combine these two types of programs. For example, as it is possible to see in the graph, first we could have a dynamic period of 6 hours with heating, then 12 hours at a fixed temperature, and then a cooling process of other 6 hours. What are the typical temperature ranges that are used in this technique? For example, from 100 to 300 degrees. This range is used to study humidity, evaporation of a solvent, for example. Higher temperatures from 500 to 600 to study the thermal decomposition of most common materials, and higher temperatures to analyze the thermally stable materials such as metals and others, but in the case of polymers, they will be thermoresistant ones. Commonly, the heating rates are of 5 to 20 degrees per minute, and according to the rate, one could understand a little bit more about the upper use temperature of a material. For example, if the heating is with a high rate, or identifying the compounds of composites if the heating rate is a little bit lower. This figure shows a typical TGA curve that shows the decomposition of different common polymers. One could learn that they have different temperatures in which the decomposition starts. For example, PBS is the one that has the lower temperature. Then we have, for example, polyethylene. Other conditions are specified in this graph, but one could see that in the x-axis, the temperature is shown, and in the y-axis, the percentage of weight loss is shown. It's also important to mention that currently it might be more useful to graph the derivative of the temperature, because it shows a little bit better when there are changes in the slope of this curve. If we compare the red line with the black line, one could learn that the derivatives show these peaks that are easier to find. Moving to the differential scanning calorimetry, represented with the letters D, S, C, is probably the most commonly used quantitative technique to study the thermodynamic properties of a material. In the graphs, we will see the so-called thermal transitions, which are related to the physical properties. For example, in the graph, we could see that there are some ranges in which these transitions occur. The first could be the glass transition, the second, the crystallization, and the last one, the melting phase, and each of them occurs at a different temperature range. In the equipment, we could have two main options, which are power compensation calorimeters and heat flow calorimeters. They are similar in the principles, but as we could see here, the changes are related to the type of heating uh, according to the objective. If one wants to keep a constant temperature, one will study the changes in the physical structure. But in the other case, one could try to keep the same type of uh, thermal flow uh, despite changes in the temperature. Regarding the applications, it is widely used in polymers to learn several properties or types of studies. Also, in modern times, nanocomposites made with polymers could also be studied through these techniques. In the left, we can see all of the cases in which this technique is used. Some of them could be very useful in the food industry as well, for example, to determine the heat capacity of a material, the enthalpies, uh, which will be important in the production phase, and so on. Regarding food sciences, here we could see several examples in which DSC have been used. For example, to understand the behavior of different gels, or to understand the melting and solidification temperatures of cheese, and the formation of alpha-lactose monohydrate during the storage of dry milk and whey powder, which is an indicator of bad conditions, or something that is very important for the chocolate industry, the polymorphic forms of cocoa butter. Since each of the polyformic forms is related to a different melting point, and one of them is the better, the fifth form has a melting point that allows the chocolate to melt in the mouth, and that is the most desired one. Also, to study, for example, the protein denaturation, enzymatic reactions, and phase changes in lipids. It's also possible to graph in the same figure both the results from the TGA and the DSC analysis, and combined they will provide more useful information regarding specific changes such as melting. The next technique is called thermomechanical analysis, and it is represented by the letters TMA. So in this technique, the changes in the physical dimensions of a material as a function of temperature due to the application of an external load or stress are measured. As we could see in the picture, a load, which is an external force, is applied on the sample, and the change in the length of the vertical length of the material could be measured both with heating conditions or cooling conditions in order to understand a little bit better these properties of the material. Always one-dimensional changes are easier to measure compared to volume changes. And in this case, the applied load is static, which means it is constant and done in only one point of the sample. It is even possible to study these changes with no external load, in which case the so-called thermal expansion coefficients are determined. This technique is also widely used to characterize polymers and almost all the other materials. The instrumentation typically has a dimensionally stable sample holder and measuring probe, programmable furnace, which will do the heating or cooling processes, a linear variable displacement transducer, which will measure the changing length, and is very sensible. A means to apply the force or so-called load uh, to the sample, and a temperature sensor, which normally is a thermocouple. In this graph, we can see the basic or main parts of this type of equipment, and the probes could be different according to the objective. If one wants to measure tension, penetration, expansion, it is possible to change these probes. What are the properties that could be understood through this technique? For example, expansion, compression, elastic relaxation, glass transitions, shrinkage, swelling, and others. As we previously said, these are characteristics of each type of material. Regarding food, for example, one could use the penetration mode of this technique to measure the coating thickness in beverage cans, for example, or to determine the softening points of waxes and fats that are used in different types of foods. Moving to the dynamic mechanical analysis, represented with the letters DMA. It is a similar study compared to TMA, but in this case, it works primarily in the viscoelastic range of a material and measure this type of properties by applying transient or dynamic oscillating loads. In the previous case, it was static. In this case, it's dynamic. So the formation of the sample under certain temperatures and other conditions is studied, and for example, alternating stress will be measured in function of time, temperature, load, or frequency. And so the viscoelastic range is located between the purely elastic and the purely viscous states of a material. The tests could be transient, and in this case, they could be classified as creep or stress relaxation. In the first case, and stress is applied and held constant, and the deformation is measured over time. In the second case, the deformation is applied and held constant, and the degradation of stress that is required to maintain this deformation is measured over time. And in the dynamic oscillatory test, sinusoidal stress is applied to the material and the strain is measured, or vice versa. Here we could see a scheme of the equipment that is used for this type of measurements. But in this technique, particularly, there are very different types of equipment that could be used, but they are a little bit similar regarding the sample processing. This technique provides information about elastic and inelastic deformation, which is known as plastic, and other important parameters such as the modulus and damping properties of different types of materials. In polymers, it is used to follow, for example, a curing process or a cross-linking process of this type of materials, as well as measuring the glass transition temperatures. It could also be a good tool to study inhomogeneous materials, which include foods. It might provide better results than DSC. For example, this technique has been used to study the processing of pasta, and it could help the manufacturers to suggest optimum cooking times, especially for their customers. In this graph, we could see that if we see these curves. The storage modules, or G prime, of cooked pasta drops very sharply at about 8 minutes at the end of this graph. So the indications for the customer will say, do not cook over 8 minutes. Finally, we can compare these two techniques that are similar in order to understand a little better their differences and similarities, and the types of results that one could get from them. Thank you.